All right, today we're going to start a new unit on sequences and series. And sequences and series are actually something that you have been dealing with in math for a long time, but maybe you just haven't called them a sequence or a series before. If you think about the term a sequence of events, that usually means something that happens first and then something happens after that, and then a third thing happens after that, and so on, and that's a sequence of events. Well, a sequence of numbers is pretty much the same thing. We might have this sequence, say 3, 7, 11, 15, and so on. And so you can see that this is a sequence where every term we're adding 4. Whenever we talk about sequences like this, we use some special notation, which would look like this for this particular sequence. A sub 1, A sub 2, A sub 3, A sub 4, and then all the way out to whatever term we would like to extend it out to, and we would call that A sub n. So what this means is that I have a sequence here that I'm calling A, and each term in the sequence is going to have a number on it for what place it happens in the sequence. This is the first term, the second term, the third term, the fourth term. So we call them A sub 1, A sub 2, A sub 3, A sub 4. And we can take that, again, we can carry it out to what we would call the nth term. And what we're going to talk about today is how to come up with a formula that will help us find the nth term. So if you look on your handout, there's two types of formulas that help us deal with sequences. One of those formulas is called a recursive formula. And so for this sequence, A sub 1, A sub 2, A sub 3, and so on to A sub n, the recursive formula is a formula for each term of the sequence that depends on the previous term. In other words, what that means is that if you want to determine what A sub 12 is, what the 12th term of the sequence is, you have to know A sub 11, or the 11th term of the sequence. So here's that same sequence that I listed on the previous page. You can see that A sub 1 is equal to 3. A sub 2 is equal to the previous term 3 plus 4, which gives us the 7. The third term is equal to 7, which was the previous term, plus 4, to give us 11. And so we could say in general that any term in that sequence, A sub n, is going to be equal to A sub n minus 1, meaning the term before, plus 4. And so really that's just a fancy, maybe actually complicated way of describing what the pattern is in the sequence. Now for this same sequence, we can also come up with an explicit formula. And what the explicit formula is a formula that allows you to directly calculate any term of the sequence that you want to know. So if we consider this same sequence that we've been dealing with, for n equal to 1, 2, 3, and 4, we know that those terms are 3, 7, 11, and 15. And so the question is, what if I wanted to find the 50th term? How could I find out that the 50th term is 199 without adding 4 50 times to get there? So what we're looking for here is the relationship between n and A sub n. Now you can see here that this pattern is actually a linear pattern because we have a constant rate of change, which is 4. And so when our constant rate of change is 4, that means that our explicit formula is going to have 4 times n. And then what we have to do is just figure out what we're going to add or subtract to that to actually get our first term. So in this example, if I did 4 times 1, well, of course that's equal to 4. And so in order to get 3, I need to subtract 1. So then we could test that out on our next term. 4 times 2 is equal to 8, and 8 minus 1 gives me 7. And so you can see that that pattern works. And so this formula A sub n equal to 4n minus 1 is much more useful to help us calculate the 50th term. A sub 50 would be 4 times 50 minus 1, or 200 minus 1, which is of course 199, or even the 1000th term. A sub 1000 would be 4 times 1000 minus 1, which would be equal to 4,000 minus 1, or 3,999. So let's see if we can come up with some of these formulas on our own. Let's look at this first example, 7, 9, 11, 13, 15. So we're looking for what's the pattern that's going on here. Hopefully you can see that we're adding 2. It's plus 2 every time. So my recursive formula, remember the recursive formula is the one that depends on the term before. In this case, if I take the term before, in order to get the next term, I'm going to add 2, because that's what the pattern is. We're just adding 2 every time. Now the explicit formula is a little bit harder to figure out, but hopefully, as you've already seen, it's much more useful. The explicit formula, let me go back to my sequence over here. So this is my first term, this is my second term, my third, fourth, and fifth. Now we said we were adding 2 every time, and if you remember in our previous example, that meant that we were doing 2 times n. It's kind of like slope in a linear formula when you're looking at a table of linear data. The common difference in the terms, that's going to be your slope, or in this case it's how much we're changing every time. But now I need to figure out, how do I get that first number of 7? Well, if n is 1, 2 times 1 is 2, and in order to get 7, it seems like we need to add 5. So I'm going to say plus 5, but then let's check it for the second term. If n is 2, 2 times n is 4, plus 5 equals 9, and that is in fact the second term. So it looks like we have the correct explicit formula. So now we're asked to find the 30th term. Well, since I have the explicit formula, I can just do 2 times 30 plus 5, which is much easier than adding 2 30 times to figure out what this term is. 2 times 30 is 60, plus 5 would be equal to 65. Now what I'd like for you to do is pause the video and try this next example on your own. So if you were successful, for your recursive formula, we should have had that each term is equal to the previous term plus 10. A sub n minus 1, or the previous term plus 10, because we're just adding 10 every time here. My explicit formula is going to be 10 times n. Since I'm adding 10 every time, it becomes like a slope, 10 times n. And then in order to get that first term of 6, we need to subtract 4. And our 30th term, if we plug into our explicit formula, we can find that the 30th term is 296. Now let's try this next sequence together. It's a different type of sequence. If you'll notice, what is the pattern here? It looks like maybe we're adding 2, but that doesn't work here. We're actually multiplying by 2 every time. This is times 2 each time to get the next term in the sequence. So my recursive formula is pretty easy. We're just doing 2 times the previous term. In order to find a sub n, I multiply 2 times whatever my previous term is. But we also need to figure out an explicit formula. And so let's think about what's happening here with these numbers. My first term is 2, and then this next term is actually 2 times 2. And then my next term, the third term, which is 8, I'm going to take my previous term, which was 2 times 2, and multiply times 2 again. To get the next term, I'm going to take the previous term, 2 times 2 times 2, and multiply times 2 again. Hopefully you can see that what we have here is an exponential situation. We have a base, here's 2 2's, and then we have 3 2's, or 2 to the third, and then there's 4 2's, or 2 to the fourth. And so what we need to do is pay attention to how these match up with our n numbers, which I'm going to write below the sequence now. Our n is equal to 1, 2, 3, 4. And so it seems like our nth term of this sequence is just equal to 2 to the n. So for example, when n is 1, 2 to the first power is just 2, and that's the first term of my sequence. if n equals to 4, 2 to the 4th power is equal to 16, and 16 is the 4th term in my sequence. So that explicit formula seems to work for us. Now we want to find a sub 30. So that's going to be equal to 2 to the 30th power, and you're definitely going to need a calculator for this one. It's a huge number. 1,073,741,824. And I did get that answer from my calculator. So pause the video and try the next one on your own. Now this example is a little bit more difficult than the previous one, so I've stopped here at this point. Our recursive formula, if you look at these numbers, hopefully you can tell that the pattern is that we're multiplying by 3. So in order to find the nth term of the sequence, if I know the previous term, a sub n minus 1, all I have to do is multiply by 3, and that's going to give me the nth term. The explicit formula, again, it's a little bit harder to figure out. But let's think about what's happening here. My first term is 4. My second term is equal to 4 times 3. Now my next term is going to take, the third term is going to take that previous term, 4 times 3, and multiply times 3 again. And to get the fourth term, I'm going to do 4 times 3 times 3, which is my third term, and then multiply times 3 again. You can see here that again we have an exponential type of situation going on. Here's 3 to the 1 power, 3 squared, 3 cubed. But if you'll notice, the exponent that we would put on 3 every time is actually 1 less than whatever our n is. In this case, it would be 3 to the 1. In this case, we have 2 3's, or 3 squared, but my nth term is 3. Here I've got 3 to the 3rd, but my nth number is 4. So your explicit formula should look like this. We're starting out with 4 times 3 to the n minus 1 power. In our previous example, it was just to the nth power because that's what corresponded with how many 2's we had each time for each term. Here, every time we have 1 less number of 3's than the number of the term. And so therefore we use n minus 1. Now for our 30th term, a sub 30 would be equal to 4 times 3 to the 29th power, because 30 minus 1 is 29. And again, this is a huge number. If you put this in your calculator, you're going to get this value. Very large number. And that's it for this video on recursive and explicit formulas. Tomorrow in class we will work the remainder of that worksheet.